Brian Swift here for Chemistry 1211K, Section 4. Today we're going to be continuing with Chapter 1, but we've jumped to, hold on, let me find it. We've jumped to Section 1.4, and we're going to be talking about measurement. We are going to explain the process of measurement, identify three basic parts of a quantity, describe the properties and units of length, mass, volume, density, temperature, and time. Perform basic unit calculations and conversions in the metric and other unit systems. We're going to be doing 1.4 and 1.5. So, measurement provides the information that is the basis of most of the hypotheses, theories, and laws in chemistry. Every measurement provides three kinds of information: the size or magnitude of the measurement, a number; a standard of comparison for the measurement, a unit; and an indication of the uncertainty of the measurement. Now, you don't have that under normal circumstances. You talk about weighing, 120 pounds. So there's your 120 is the number and pounds is the unit. But you don't say plus or minus 2 or 3 pounds. But the best numbers have an indication of uncertainty. And implicit in that 120 pounds, though, is a measure of uncertainty, and where you stop the counting of the digits. So if you're only using 3 digits, then you know you're not certain to the 4th digit. Without units, a number can be meaningless or confusing. In chemistry, we use an updated version of the metric system known as the International System of Units, or SI units, used since 1964. Of course, in ordinary life, we use the English system, which is absolutely horrible in terms of units. The metric system uses factors of 10 and is much more mathematically friendly and friendly for mental computation. Okay, so in the metric system, length is the meter with the symbol lowercase m. Mass is the kilogram, or kg. Time is the second, or s. Temperature is Kelvin, or capital K. Electrical current is the ampere, or capital A. Amount of substance, chemical substance, is the mole, which we just dropped the E for the symbol. And I don't know why they picked the luminous intensity as the candela, or the CD. We're going to be using moles to a very large degree. And there is a lot of history behind that, which includes electrical current. How do we know what we know about things? And there's another unit of temperature, which we'll be getting into in the next lecture. It's Celsius. So Kelvin and Celsius are two metric systems of temperature. Second is intuitive. Kilogram is 2.2 pounds, and the meter is about 39 inches, a little bit greater than a yard. Okay, this is a very, very important table. In fact, I'm going to put this table into D2L. This is something you've got to memorize. The metric or SI units and their prefixes and what factor they represent. You've heard of kilograms. Well, that should be on the next page. You've heard of kilograms, and you've heard of centimeters, and perhaps you've heard of milliliters or microliters, nanoseconds, and some of these others are less commonly used, pico and femto, mega millions, perhaps you've heard of that, and gigawatts from Dr. Brown and Back to the Future, but tera for terahertz. Anyway, these are the prefixes you are going to have to know. The common SI base unit, length. The International Scientific Unit of Length is the meter. It was originally intended to be 1/10,000th of the distance from the North Pole to the equator. A meter is now defined as the distance light travels in a vacuum in 1/299,792,458 of 1 second. Very, very close to 300 million meters a second, or 3 times 10 to the 8th meters a second. It's a little rounder in centimeters. It's 3 times 10 to the 10th centimeters per second. A meter is about 3 inches longer than 1 yard. Okay, the relative lengths of 1 meter, 1 yard, 1 centimeter, and 1 inch are shown. Not actual size, so it doesn't do us any good, really. As well as comparisons of 2.54 centimeters and 1 inch, and 1 meter and 1.094 yards. So, the relevant number to get out of this is 2.54 centimeters to 1 inch. That they are the same, and 1 meter is almost 1.1 yards, 10% greater than a yard. Okay, the SI unit of mass is the kilogram. A kilogram was originally defined as the mass of 1 liter of water. It is now defined by a certain cylinder of platinum iridium alloy, which is kept in France. And every time it's polished, the definition changes a little bit. 1 kilogram is about 2.2 pounds. They have just changed the definition of the kilogram to a sphere of silicon, of isotopically pure silicon. And it's significant in a lot of ways, not significant to you, though. It means that we can now make standards based on that definition instead of relying on this 1 platinum iridium alloy cylinder. This replica prototype kilogram, so it's not the real kilogram, it's a fake kilogram, is housed at the National Institute of Standards and Technology in Maryland. So it's not the real French one. Okay, the SI unit of temperature is the Kelvin. No degree word or symbol, the little superscript lowercase o, is used with Kelvin. The degree Celsius is also in the SI system. Celsius degrees are the same magnitude as those of Kelvin, but the two scales place their zeros in different places. Water freezes at 273.15 Kelvin, or 0 degrees C, and boils at 373.15 Kelvin, or 100 degrees C. The SI unit of time is the second. Smaller and larger time intervals can be expressed with appropriate prefixes, like nanoseconds. Alternatively, hours, days, and years can be used. We can derive many units from the 7 SI base units. Volume, the measure of the amount of space occupied by an object. The standard SI unit for volume is the cubic meter. In crossword puzzles, it's called a steer, which is derived from the SI base unit of length. Other units for volume are the liter, which is what we're going to be using most, and the milliliter. They've got, if you actually take a 1/10 of a meter and you make a cube out of it, its volume is 1 liter. If you take 1/100th of a meter and make a cube out of it, its volume is 1 milliliter. The relative volumes are shown for cubes of 1 meter, 1 cubic meter, 1 cubic decimeter, and 1 cubic centimeter, which is the 1 cubic decimeter is also 1 liter, and the 1 cubic centimeter is also 1 milliliter. Not to scale. The diameter of a dime is compared relative to the edge length of a 1 centimeter cubed, 1 milliliter cube. So a dime is a little bit more. It's 1.8 centimeters across. Now, density is the density of a subject is the ratio of the mass of the sample to the to the mass of a sample of the substance to its volume. Now, of course, if you double the mass of the substance, you'll double its volume, and therefore the density remains the same. The standard SI unit for density is the kilogram per cubic meter, kilogram per meter cubed. But you can have other commonly used density units on a state of matter, grams per cubic centimeter or grams per liter. Air is like 1 point something grams per liter. Measurement uncertainty. Okay, so we've gotten through unit 1.4, we're into 1.5. Measurement uncertainty, accuracy, and precision. Okay, something that's going to be very big in this course, something that's going to run you ragged, is significant figures. Now, this is not the unit in which we are going to be, well, anyway, significant figures will be very important to this class. Counting is the only type of measurement that is free from uncertainty. So integers, if you say you've got 1, 2, or 3 things of something, you're stating it absolutely. The result of a counting measurement is an example of an exact number. The numbers for defined quantities are also exact. So 1 foot is exactly 12 inches. 1 inch is exactly 2.54 centimeters. 1 gram is exactly 0.001 kilograms. Quantities derived from measurements other than counting are uncertain to varying extents. These numbers are not exact. There are always practical limitations of the measurement process used. A measured number must be reported in a way to indicate its uncertainty. In general, when recording a measurement, you are allowed to estimate 1 uncertain digit. To measure the volume of a liquid in this graduated cylinder, you must mentally subdivide the distance between the 21 and 22 milliliter marks into tenths of a milliliter, and then make a reading, an estimate, at the bottom of the meniscus. So if we look up here, the 21 and 22 marks are on the graduated cylinder, and you must estimate right here, it's a little bit over half, so half would be 0.5, so let's call that 21.6 milliliters is contained in that graduated cylinder. On the previous slide, if one recorded the volume in the graduated cylinder to be 21.6 milliliters, 2 and 1 are certain digits, 6 is an estimate. Someone else might perceive the volume to be 21.5 or 21.7 milliliters. All the digits in a measurement, including the uncertain last digit, are called significant figures or significant digits. Frequently, we need to know the number of significant figures in a measurement reported by someone else. These numbers are always significant. Non-zero numbers, captive zeros, and trailing zeros when they are to the right of the decimal place. That's when you write like 0.100, and when they're in scientific notation, like 1.500 times 10 to the fifth. These numbers are always not significant. Leading zeros, like 0.00100, the zeros getting up to that 1 are not significant. And trailing zeros when they are to the left of the decimal place. So, okay, I might have, yeah. That's right. When I've said something wrong up here. When they are to the right of the decimal place, that would be like 11500 point. So those zeros are significant as soon as you write the point. Hold on. These numbers are always not significant. Trailing zeros when they are to the left of the decimal place. Trailing zeros when they are to the right of the decimal place. Okay, we'll work on that. Okay, here we go. This 0 is captive. It's between the 3 and the 9. This one is trailing. These are leading, and they're not significant. This one's captive, and this one's trailing. Results calculated from measured numbers are at least as uncertain as the measurement itself. When we add or subtract numbers, we should round to the result to the same number of decimal places as the number with the least number of decimal places. So we've got lined up, 1.001 and 1.1, and we add those together, and we're going to get 2.1. The 001 is more precise, but it gets wiped out by the one that is less precise. When we multiply or divide numbers, we should round the result to the same number of digits as the number with the least number of significant figures. Okay, so if you multiply something that has 4 significant figures times something that has 5 significant figures, the result should be in 4 significant figures, the smallest number of the two. That's when you multiply or divide. So the rule for adding means that you put the point there, you line up the point, the decimal point, and the one with the fewest number of decimal places is the number of decimal places in the answer, and when it's multiplied or divided, the fewest number of significant figures is the number of significant figures in the resulting answer. If the digit to be dropped, the one immediately to the right of the digit to be retained, is less than 5, we round down and leave the retained digit unchanged. If it is more than 5, we round up and increase the retained digit by 1. If the dropped digit is 5, we round up or down, whichever yields an even value for the retained digit. The following examples illustrate the application of this rule in rounding a few different numbers to 3 significant figures. So 0.028675 rounds up to 0.0287. The dropped digit 7 is greater than 5. 18.3384 rounds down to 18.3. The dropped digit 3 is less than 5. 6.8752 rounds up to 6.88. The dropped digit is 5 and the retained digit is even. 9.285 rounds down to 92.8. The drop digit is 5 and the retained digit is even. A measurement is said to be precise if it yields very similar results when repeated in the same manner. A measure is considered accurate if it yields a result that is very close to the true or accepted value. These arrows are close to both the bullseye and one another, so they are both accurate and precise. These arrows, for B, are close to one another but not on target, so they are precise but not accurate. And these arrows are neither on target nor close to one another, so they are neither accurate nor precise. These are the volume of milliliter cough medicine delivered by 10-ounce dispensers. Dispenser 1 is precise but not accurate. Dispenser 2 is accurate but less precise. Dispenser 3 is both accurate and precise. Okay, what I want to do is go back to this slide. These numbers are always significant. Trailing zeros are significant when they are to the right of the decimal place. I would say to the left of the decimal place, because as soon as you put that point, you're saying that it's significant. If you don't have the point there, it's debatable whether they are significant or not. Whether it's 10,000 all significant or not. Okay, when you have to the left of the decimal place, when you have these numbers are not significant to the right of the decimal place. That's why we put the decimal. Okay, I've got it. We put the decimal place in there. Okay. Anyway, we'll work this out later. I may have to redo this lecture because of this this thinking. But thank you very much for listening. We will talk later. All right. Escape. Boom. And